Okay, let's get started. This is my last lecture, and I definitely prepared way too much stuff, so I'm just going to try to jump around and tell you maybe a few fun things, hopefully, and we'll see what we get through. Now, remember, before in the previous lecture, I had just finished talking about these electromagnetic couplings of the dark matter, right? Axion, Earth, hidden photon, and how you could drive resonant experiments, for example, and some ways to look for the dark matter electromagnetically. There's really lots of other ways, but I couldn't possibly begin to talk about all of them, so I'll refer you to literature. There's a lot of great ideas. People have really been having a lot of ideas recently, in fact, especially with electromagnetic detection. So I didn't quite get to finish what I wanted to say, though, which was I wanted to show you the sensitivity plot. So here's a sort of simplified kind of cartoon-esque sensitivity plot. This is the photon coupling of the axion versus the mass. And these are some astrophysical limits. Let me not even say where they come from. Yeah, I think you'll hear in future talks. And then these two kind of blue and brown and gray blobs show the sensitivities of the experiments I was just talking about. Up here on the right, these are the microwave cavity experiments. As promised, they're sort of around gigahertz, right? Give or take 1 or 2 orders of magnitude. The gray is what's been done, or actually that was a little old, out of date. Some of the brown has already been done. The brown was the next step, and the blue was some sort of projection for what could be done in the future. But then we said, so these are great experiments for looking around the microwave cavity frequencies. But as you go lower, you'd have to build far too big a cavity. That doesn't work, so we want to go over to a lumped element, or it just means like an LC circuit kind of detector, right, where the resonant frequency is not set by the physical size of the thing. Because obviously I need to have a resonant frequency far below the light travel time across the device. And so this would be examples like the aptly named LC circuit experiment, abracadabra, or DM radio, for example. This is, again, some projection for what they might be able to cover in the future. And just remember, these are all resonant experiments. So actually, at any given time, they're just very narrowly homed in on a single frequency. So they're just one spike here. That's why these gray, the actual limits, look like this, right? They're individual, very narrow spikes. In fact, sort of about maybe 10 to the minus 6 wide or so, or a little wider. The 10 to the minus 6, if I haven't said it before, comes from the fact that the virial velocity of dark matter is 10 to the minus 3. So the kinetic energy of dark matter is 10 to the minus 6 of its mass. So that means the dark matter is actually, it's not a single frequency. It's actually a narrow line whose width is about 10 to the minus 6. So that's sort of the signal you're looking for in these resonant experiments. Just to explain a few of the features, so the sharp cutoffs on the edges and frequency are just at some point you'll stop the scan. So since these are resonant, they're really just sharp. They're just very narrow lines that you just move. You scan in frequency. Sometimes people are confused by this funny-looking diagonal line. So this diagonal line of the sensitivities is not an accident or something. It's an absolute choice. It's a choice because you see this red stripe here that I've labeled the QCD axion. I'm going to mention that in just a second. Actually, you hear much more about that in other people's lectures a little bit later in TASI. But that's a nice, well-motivated, strongly motivated part of parameter space that we'd like to get to. And so experiments will simply choose, generally, to spend enough time to get down there to cover that band at each frequency and then move on. So that's why the lines are sloped like this, OK? Is that clear? Is that OK? Question? Yes?
When do you think you'll reach the QCD axion line? And what steps do you need to take to get there?
Great question. I think the right answer is definitely nobody knows, for sure. Well, to be fair, so ADMX has already probed it, right? It has for many years, which is fantastic. So that's a great experiment. It's ongoing, and there's other microwave cavity experiments too that are getting close. So some of the experiments have already probed it. But let's say to cover these, and then the first iteration of, for example, the lumped element experiments wouldn't go all the way down to the QCD Axion line. They'd cut out some big chunk here of Axion-like particle parameter space. But to either improve the cavities or take all these and cover higher frequencies, or take all the lumped to develop the lumped element technology down to get to the QCD Axion line, I think that's let me say I'm an optimist, so I think it's absolutely doable, but it's definitely challenging. And in fact, I think it's fair to say that most people believe it would require some significant R&D. It's not just dollars and person hours. There's some R&D, some science that has to work. And in particular, we think we probably know how to make the resonators, but one of the key pieces of magic in all this that I've glossed completely over is the very high sensitivity magnetometer you need to read it out. Right, so the resonator, sort of, if you like, a simplified way to say it is it amps up the signal, but then I still need some really sensitive measuring apparatus to see it. So people are actively at work developing. So this is the whole field of quantum sensing, as you may have heard. As you know, the word quantum is very big these days, very hot. Brings you a lot of money. But there's even some truth to it. So, for example, to push the cavities up higher in frequency, most people, I think, believe you're probably going to have to, well, you are going to have to develop new sensors. So, for example, some way to reliably count photons without losing too many and without introducing noise. So really see if there's one photon in my cavity or not, which is a tall order. So some quantum sensor photon counting technology there. And similarly here, people, including actually my collaborator, Kent Irwin, who's an experimentalist at SLAC, is funded to and is developing or attempting to develop. And if you like, let me just call them better squids. He would not like that name because he sees all sorts of differences between the way you build these things. But he even has some god awful mouthful of a name for them. But essentially things to push to and past the quantum limit. So I think that's really why I don't want to guess a year, because it's one thing if you're just building on a schedule with the dollars or something, but if you have to do science, it could work or it could not, right? We hope it'll work, and there's been a lot of promising preliminary results, but I won't, I won't get, maybe other than to say that I believe it's within my remaining lifetime. All right, I hope. Yes?
Why is the Axion band a band rather than a line?
Great question. And in fact, really, honestly, I should have, I was just yelling at Kent the other day for not doing this, but I did it here too. I shouldn't even have drawn it as a sharp band. It should just fade out. I won't talk about this, although I think Ben or someone later will talk about Axion model building. Well, I'm going to tell you just in a second, just very briefly, what the QCD Axion is. So that would have a defined particular, for a particular mass, it would have a defined particular coupling to QCD. But it doesn't even actually have to have a photon coupling at all. That's not required by the coupling to QCD. It would be a fine tuning, but you could tune it all the way to 0 or something. That's a little perverse. But more reasonably, there would be a large range of UV models that could give rise to the Axion. You may know there's the famous 4-letter acronyms DFSZ and KSVZ, and KSVZ uses heavy quarks. So I'm not going to talk about the model building. Let me not get into it. It's a nice long story. I believe you will hear about it later. But for example, how you charge those heavy UV particles would change order 1, well, unless you do some funny tuning or some other funny model building, but order 1 change the strength of the coupling to photons. So that's the sort of UV model dependence, if you like. Turn it around, if we can measure this, if you give me my dream scenario, we can see this, we can see the QCD coupling, we know the mass, if we get a detection, we will know the mass. Then you actually learn something about UV physics, which is pretty cool. I mean, really UV physics, not TeV, but very high F. Yes?
So let's say you hit this QCD target and then you measure it and you find it. How do you know it's the QCD Axion and not some other Axion?
Good, you don't. You definitely don't. One of the reasons I would like to measure as many couplings as possible the Axion, that also just tells you as much as possible about the new physics, the UV physics from, could be, if you see an Axion, here-ish or something, it's coming from the gut scale, for example, 10 to the 16th F. So that's a really cool scale to learn about. That would be neat. We're not going to build a collider that gets us there. So absolutely. So I'd like to measure as many couplings as possible, including, for example, the coupling to QCD, which would be the defining coupling of the QCD axion. And that's what I'm about to tell you about, how you might go looking for that coupling, for sure. But you're absolutely right, you don't. And in fact, there's even, as I mentioned, I think yesterday, there's even something a little bit worse. I'm sort of talking like you could measure the couplings here, but you can't. Remember, it's always G root rho. So you just get the overall amplitude of the signal, G times square root of dark matter density. If you believe what you've seen is all of the dark matter density, then I know that number. Well, actually, I know it up to a factor of 2. We don't know exactly our local dark matter density, but OK, good enough. But you don't necessarily know that what you've seen is all the dark matter, right? Nothing tells me that, so all I actually get is the combination G root rho. So I won't even really get the couplings. Although I will, if I see it in multiple experiments, get ratios of couplings, which is already interesting. But that's a hard thing to know. In fact, as a little bit of a tangent, you would have to do a non-dark matter experiment, like an axion transmission experiment, like a light through walls or something, to really get the couplings, to disentangle that degeneracy. Good, yeah, great questions. Any other questions on this? Yes?
Is there any simple reason why the astrophysics students are usually upper compared with other lab-based?
Why they're up there? Well, you know, I'd say the real reason is you work out the numbers and that's where it comes out. By the way, they're really not super related to these limits because these are limits on the axion in the Lagrangian. So they come from, if there exists an axion in the Lagrangian, whether or not it's populated in the universe doesn't matter. It would be radiated out by stars, for example, do all sorts of funny things. Whereas these come from dark matter. So they're really not too parametrically related, I would say.
It looks like the ground-based detections depends on the math, but astrophysical limits cover a lot of.
Very good. Yeah, this is something I hope Ben will talk about more. But yeah, I can tell you roughly the reason for the shape. So these things, for the shape of these resonant detectors, you should think these narrow little lines and bands. They're really fingers sticking down like this. For the shape of this, you should think something up here, but up top of the plot, but broad, stretching across all the frequencies. They so go different ways. This one's a rectangle that goes this way. The astrophysics is a rectangle that goes this way. The resonance are a rectangle that goes this way, sort of. And the reason to understand that you can understand. So I just said why these are narrow lines. I'm looking at a particular frequency. I have to scan it. These, however, are production of the axion in the star. The star is hot. It's happy. It does not care about the mass of the axion. It's happy to radiate any axion whose mass is less than the temperature of the star. So for example, if this comes from supernova 1987A, temperature was 30 MeV, capital MeV. I don't have capital MeV on this plot. So this will go all the way out, over here to capital MeV and then cut off. So you get and it just doesn't. Other than that, it only cares about the strength of the coupling. That's the strength with which the axion can be produced. It's very light compared to the temperature of the star. So these are all highly relativistic axions streaming out, and they don't care about the mass. So absolutely, very good. Yeah, good observation. Yes.
Where does then the slope come from?
This one? Great question. So really, you should think of this as. So I hope Ben will talk about some of this. Let me just say, you should think of this as one big flat line, and actually that can be due to the CAST experiment, which isn't quite an astrophysical limit, but let me be vague. And then some of these are, I would say, a little bit more controversial limits. I've chosen to plot them here, but it's questionable to some extent. They depend on axion-photon conversion coming from various different astrophysical objects. And you get things like, oh, my photon would have gone to an axion and I would have lost it and not seen it, or would have come back and I would have seen it when I shouldn't have seen it, various limits like that. But that conversion, as I'm going to definitely hope Ben will talk about, is heavily dependent on, you have to convert with a magnetic field background, right? That's what I just told you that. Well, we don't really know the magnetic field in the rest of the universe. I know the magnetic field here. That's where we measured, and that's we have much poorer experimental understanding of the magnetic field other places. And you have to make some assumptions about not just the overall strength of the magnetic field, but its coherence properties and things like that to get the axion conversion. By the way, actually, that one point is actually a point I wanted to make when talking about the direct detectors, which is whenever you're doing axion to photon conversion, for example, axion dark matter comes in and becomes a cavity excitation, or for example, in astrophysical situations, the axion actually won't convert, or the photon and axion won't mix with each other, won't go back and forth, convert to each other, off of a dead homogeneous magnetic field. So this is why the coherence length, the coherence properties, the gradients of the magnetic field come in. And it won't do that. You can see that because, well, there's multiple different ways to say it, but one fairly simple way to say it is the photon is a massless particle and the axion has a mass, yeah? So the dispersion relations do not match. You can't just change a massive particle to a massless particle and vice versa, right? Not for one. You can't conserve energy momentum that way. The momentum is wrong for the same energy. In particular, it's going to do any of your, any wave crossing a boundary, yes, like you did in freshman physics a long time ago. It always keeps the same frequency, right? So the axion to photon conversion will convert to a particle of the same frequency. But then the momentum will be wrong. So how do you conserve momentum? And the answer is you had to have a gradient somewhere. You had to have some spatial translation breaking. So for example, in ADMX, or the experiments I was just telling you about, they could even have a dead homogeneous field, but the spatial translation breaking comes from the walls. Okay? It's not completely obvious. You have to work through the equations to see it, but that's what's going on. Or in astrophysical situations, it could be a gradient to the magnetic field, or a change to the magnetic field that's producing it. So you really need those gradients, or you will not get this conversion. And so that makes these limits trickier to know. Anyway, that was a long tangent. Great questions, though. Good. Yes? Question or no? OK. All right. OK, so that was what I wanted to say about electromagnetic detection. There's tons and tons more, probably thousands of papers written on this, so can't possibly summarize it all. So back to my favorite little chart of all the couplings. So I've told you about essentially all of them. Told you a little something about essentially all of them anyway, except for this one here. So now let me get to QCD, OK? And in particular, as we just said, this is the defining coupling for the QCD axion. So it's an important one. So let me, in case you don't know or don't remember what the QCD axion is, I'm really not going to tell you that. I think you will hear in later lectures. But I'm just going to give you a tiny, brief little intro to this, just so you can understand the phenomenology I'm going to talk about. OK? And the intro goes as follows. First, as you may have heard, in the Standard Model, we have this famous problem called the strong CP problem. In very brief, that problem is the statement that, well, it's actually completely allowed by all symmetries to write down the term theta GG dual in the Lagrangian of the Standard Model, okay, where G is the field strength of QCD. What does that do? And theta is a dimensionless parameter, okay? Now, I don't know what strength theta should have. In principle, it could be 0, but there's really no reason for it to be 0, right? That operator is allowed. OK, now, but however, this one has a very important physical effect, which is that this one famously produces an electric dipole moment for any nucleon. All nucleons will pick up an EDM, which is proportional to theta. And the very rough size of the dipole moment of the nucleon is about 3 times the minus, so it's very small. It's about 3 times the minus 16 times this dimensionless number in e centimeters. If you haven't heard the unit before, don't worry about it anyway. That's the unit in which we usually measure dipole moments, right? So the dipole moment is produced by this is very small, but we're really good at looking for EDMs of fundamental particles or of nucleons, okay? And so experiments have set only, we've never seen it, of course, famously, and set upper limits, which require that theta be less than about 10 to the minus 9 or 10 to the minus 10. And that's the strong CP problem. This thing that should be there, why does it appear not to be there, at least down to some exceedingly small level? Or another way to say it is 0 wasn't at all a special number for this parameter, so how the heck did it end up so close to 0? Yes?
Something that's always confused me about this is like theta has to have some value, so why shouldn't it be very small?
Could be, but it looks like you threw a dart randomly at a board, and you weren't aiming at all, and yet you hit the bullseye to within 10 to the minus 9. If you saw that, let's say someone said to you, I'm in a bar, we're all drunk, and I'm going to bet you that I won't aim at all. I'll look this way, and I'll just throw the dart, right? And if they still hit the bullseye to 10, and you can move the target wherever you want. So 0 is not a special point. The person can't know before they close their eyes, right? And they still hit the bullseye. Then you'd think they were probably cheating. You'd think there was some dynamics going on that they weren't showing you, right? So that's the strong CP problem. It's not a logical impossibility, but it's a hint, we think, maybe, of some dynamics going on under the surface that we may not be seeing. Yes?
You could say the same for any value, right? If theta is much like 2, then you would say
Well,
2 is the bullseye now.
well, but I would say 0, however, is otherwise a special value. It's a physically special value. So 0 is defined. It's meaningful, okay, because it creates this nucleon EDM, right? But there just was nothing about the high energy Lagrangian that knew anything about 0. There was no symmetry that liked 0. So that's what's weird, that it was the bullseye, not a random point. But you can think what you want. It's not a logical impossibility that it's just really small. Yes?
Could you say the same for the electron Yukawa, though?
Absolutely, and definitely agree. That one's 10 to the minus 5 instead of 10 to the minus 9, but absolutely. And that has motivated hundreds or thousands of papers on making flavor models of Yukawas. Absolutely. For sure. Definitely. I also believe that's important. But I sort of dropped out of favor recently, but I still like it. Or dropped out of popularity. Okay, so that's all I'll say about strong CP model. I think you'll hear a lot more later, but let me move on. This is not what I want to talk about. The Axion solution, so there's different possible solutions, but the Axion one is a nice, really simple one. The Axion solution takes this would-be fundamental constant of nature. You'll recognize the words here. Takes this would-be fundamental constant of nature and turns it into a dynamical variable, something that can change in time. So it turns, in other words, into the field A, and we usually write A over F. Okay, where F is some just dimensionful number, just some parameter. Great, okay, but the real magic, which I'm not going to tell you about, is that when you do this through the magic of instantons, you produce a potential for the axion. Whoops. That was badly drawn. The key part about this potential is that it's minimized at 0, where 0 means 0 physical. So the axion a priori has a shift symmetry. So you could ask that, which is why I said there's no symmetry that sets this to 0. You could ask, what do I mean by 0? But I mean, amazingly, the physical thing that the nucleon EDM is 0 here. That also matches up with the 0 of the axion potential. I'm not going to tell you how that works. I hope you'll hear that later. However, the Axion solution then is, well, the axion is produced, starts some value in the early universe. This is the famous misalignment production, for example. But then it'll oscillate back and forth like we've been talking about for these many lectures. And it'll damp down, it'll redshift with the expansion of the universe, and it'll eventually get to be very small. Okay? So it'll get to be very small, and then this is the effective theta value, A over F. And so then that solves the strong CP problem. Okay? Only, I would say, that then suggests an interesting experiment to you, which is, well, it's small, but it's not 0. It's these small residual oscillations, which are the dark matter. That's what I've been talking about for the last 3 lectures, right? The dark matter field oscillating its potential. That's the energy density. And this, did I write it down? Yeah. The mass of the axion goes very roughly like the QCD scale squared over this F axion, and this F axion has to be a very large number, so this is a very small mass. So it is indeed an ultralight dark matter particle. And in fact, so I should pause there. This is the Axion solution to the strong CP problem. Okay, is that good so far? Okay, but then the idea said very simply, the signal you could look for of this, so I have my axion coupling to QCD, right? That's my last coupling that I want to look for. The signal I can look for is, well, look, the axion is oscillating with this frequency, right? This is a very low frequency. It's maybe megahertz or gigahertz, but it's very low compared to any of the relevant scales here, which are the QCD scale. Okay? So it's QCD instantons, for example, which are creating, things like this. So, as far as QCD is concerned, this oscillating axion might as well be static, yeah? Everything happens on QCD frequencies. During a QCD timescale, the axion doesn't move, doesn't change field value, yeah? This is the adiabatic approximation, in other words. So therefore, I know immediately that this operator must have the physical effect of producing a dipole moment, an EDM, for all the nucleons of the world. And in place of theta, I just sub A over F. Okay? Only now, This EDM will not be a fundamental constant of nature. You see the theme here in these lectures, right? It'll be, you thought it was a fundamental constant of nature, the EDM of the nucleon, that's something that people have talked about for decades, right? But no, it's an oscillating number. It's an oscillating parameter. And so, by the way, as a consequence of that, people have been looking for it all wrong. They've been looking for a static experiment. They integrate for days or weeks or months. Integrate right over all that oscillation and average it out to 0. So none of the previous experiments looking for, very precise experiments looking for nuclei EDMs, looked for this signal correctly. Okay? Is that clear? Is the signal clear? Questions on that? Say again, sorry?
Are there experiments looking for this oscillation?
There are now. I'm gonna tell you that. Yeah, exactly. So this was where once we realized there could be this kind of signal, then start talking and how do we design experiments exactly. So that's the key idea. This is the signal that I want to go looking for. Now, as he says, now I want to see, okay, can I design experiments to look for it, right? And you maybe have some hope because nucleon EDM experiments are some of the more precise experiments that humanity does. So maybe I can kind of repurpose some of those same techniques. Okay, I think, oh, sorry, one more very important thing. It's staring us in the face here. Remember I just said, when we were doing electromagnetic detection, I just said, oh, that theta FF dual, that's a total derivative. So remember our effect had that nasty suppression factor as m went to 0, right? It was a total derivative, right? So it had to decouple in the limit that this cosine just becomes a constant, right? When the frequency goes to 0. Look, I found an effect that does not, right? This is a physical observable, the nucleon EDM, and it just goes like theta, just goes like a over f, not a derivative of theta, yeah? Not a derivative of a over f. You see that? Do you buy that? Do you believe that? Kind of slipped that under the rug there. I just said some things about adiabatic, and out that came. In fact, actually, so this is true, and it's a key property. In fact, what really first got us very excited about this, because we finally found a non-derivative effect of the axion. Even though the axion's a pseudo-Goldstone boson, we finally found a non-derivative effect of the axion that won't get small as you go to low mass. And so this, I think, will be the way to look for axions at low mass. Okay, the other things are good at higher masses. This will be the way to look at low mass. And I'm going to show you in a second how that works out on sensitivity curves. Is that clear? Yes? In reality, it's a practical question, can I make technology sensitive enough? But basically, actually, I mean this. These things work down to, you can see 10 to the minus 7, 8 EV for the QCD axion, but I want to go all the way down to 10 to the minus 12. So how am I going to do that? I said it was going to take many years even to get here. It looks fairly hopeless to get all the way down there. This is the way. Yes?
Is there a theoretical lower bound on the QCD axion mass?
Yes and no. So a sort of soft lower bound is we're not entirely sure what it would mean to take f above the Planck scale. And so that would set a lower bound on the mass.
Gotcha.
Although you could maybe get around that as well. Yeah, good question. Now there's one, yes?
Experiments where doing measurements and averaging over like weeks or months.
Mm-hmm.
Is this theta and the negative noun from phi?
Yes, exactly. If you want to look for, if you think you're looking for a fundamental constant of nature, right? First of all, don't look for something that's oscillating. Look for a constant. And second of all, spend more than 1 second taking data, right? You want to spend weeks and months and set the world's best limit, some of which was just set here, by the way. These are some of the best experiments just down the hall. Exactly. So none of those will directly apply, although similar ideas could potentially be very sensitive. Now, one last point that might be confusing you, which is I just made a whole lot of noise about how this is great. This is not suppressed at low mass. It's not a derivative effect. But GG dual is a total derivative, though. Same as FF dual, OK? So what happened? Well, you could have asked that same question up here. Wait a second, GG dual is a total derivative. How did I ever get a physical observable consequence of a total derivative operator in Lagrangian? Again, that's the actual fact that I'm not going to tell you about, so I'll just say through the magic of QCD instantons. But just be aware that that's a highly non-trivial effect, and then hopefully you'll hear about this a little bit later in this summer school. OK, so we just, when you first write down this formula, you just sort of accept it. Okay, it's proportional to theta. No, that's a highly non-trivial dependence right there. There was no derivative making theta go, making this whole effect 0. Okay.
Integrate the parts with the derivative of the axion.
Yeah, so for an oscillating axion, it would have been okay. But notice, this was a total derivative, and this actually has a physical effect. And it's that same fact, why this doesn't have a derivative on it. So for the FF dual, exactly, you integrate the parts, put the derivative on the axion, and that's why you can see all effects have to be derivative effects, which is also what you expected for a pseudo-Goldstone boson. This one breaks it. This is the pseudo in the pseudo-Goldstone boson for the axion. This is the non-derivative operator. Okay, very good. Yeah, great questions. Any other questions? Yes.
Shouldn't you have like a lower limit on the mass though? Because if the action is really light, it has to relax to the the lifetime of the universe, and then otherwise you will get a really large.
Very, very good. Absolutely, yeah. If I wanted to solve the strong CP problem, then absolutely, definitely. Now, if I set f to m Planck, I end up about here, which is a frequency of about 100 hertz or so. So the period is 100th of a second. So no problem relaxing. But if I did try to make a model where f could go way, way, way beyond m Planck, then you're absolutely right. That's a great point. That would be a bound on your ability to solve the strong CP problem. Now, I am not aware of models which convincingly solve the strong CP problem with higher f's, although I could have missed something. But definitely, yes, I like that. Yeah, it's good. That's a physical one. Yes?
A lot of axion papers and even out papers, you see kind of like a preferred zone of like 10 to the 9 to 10 to 12 for FA. Wondering where that specific desired zone comes from.
That comes from, I would say, so now you'll get my personal prejudice. Other people will disagree, I promise you. I have disagreed with them many times over the years, in many reports and other things. I would say that comes from a sort of theoretical prejudice. So what it really comes from is the production mechanism. So where you think the production mechanism can produce order 1 of dark matter. However, essentially any of the production mechanisms we use for the axion actually could produce order 1 of dark matter anywhere in this mass range. For one of the production mechanisms, the misalignment mechanism, if you believe that one of the parameters, the initial misalignment angle, is order 1, although then you have to take f, the dimensionless f, much smaller than 1, so I don't know why to prefer that combination. But if you do, then you tend to get in this range. Or there's another option, which is one definite possible option, but it's certainly not the only thing, which is that if PQ symmetry breaks after inflation. So I'm not going to talk about production mechanisms at all. I just thought about it, but I didn't have time. I'm happy to tell you this story in much more detail and gory detail later, because there's actually a really cool story here with inflationary quantum perturbation-produced fluctuations of the axion, of the QCD axion even itself, which we had, my student Adam and I had figured out a couple years ago, which was a lot of fun. But in any case, let's say, I would say that in fact you can trivially produce the whole mass range and get the right dark matter abundance, although people would disagree. Yes?
So this experimental effort, it's an upper bound, right? The neutron medium.
That's the upper bound. Yeah, theta less than 10 to the minus 9-ish.
Right.
Yes.
So should it be rigorously 0 if there was an axion?
Great. No. So actually, no, for 2 reasons. So first of all, it's not 0 because it's this, but this has no. So let me write this out again. This is A naught. No, sorry. The upper bound is this, so it's 10 to the minus 9 times 10 to the minus 16, so it's 10 to the minus 25. This is the result of a theory calculation. Yeah. So if there's an axion, this is the EDM. So all our nucleons, if the axion is the dark matter, then all of our nucleons have this as their EDM. It's funny because it's oscillating in time. It's not it's got an amplitude, but it's a number that keeps flopping between positive and negative or whatever. So they'll have this. This doesn't have this oscillates around 0 uniformly, right? That's the axion created effect. Actually, I didn't discuss it. You may hear about it later. This potential will also have a small shift off of 0. So there will be plus a constant term, and that's set. The minimal amount of that is set by the amount of CP violation of the standard model. But let me just say that and not go into it more. It's, however, a very small EDM. So that looks, it's quite far from our current experiments. It would be a sort of holy grail of looking for static EDMs.
Even on average, it will not be 0.
That one's not 0 on average. That's right. That potential is shifted off of 0 a little bit by the CP violation of the standard model. Yeah. Otherwise, it would average to 0. There could be new physics at the TeV scale, for example, that makes that bigger also. So the people looking for electric dipole moments often phrase their limits in terms of how far in energy they probed above the TeV scale, for example. And they can go some orders of magnitude, which is pretty cool. Those EDM experiments are one of the most precise we have. All right. Good. So now let me tell you very briefly about an idea we had to use this coupling to look for the QCD axion in this low mass range that we called CASPER, this cosmic axion spin precession experiment. And the basic idea was as follows. Well, this thing, the axion, this coupling of the axion, the GG dual coupling, produces an EDM, right? I didn't quite say it, but the EDM it's a dipole moment. It has a direction, right? It points in a direction. Well, a nucleus has no direction other than its spin, so it has to point along the spin of the nucleus. Okay? Well, that means the cool thing is we've developed a lot of technology that loves to talk to nuclear spins. In particular, this NMR technology, right? The heart of MRI machines has been developed and developed and developed over decades because those things are really valuable to us humans, right? I've been in MRI machines many times. So there's been a lot of work and a lot of money invested in it, and by now they've really done some amazing things with NMR techniques. I won't even possibly get to tell you all of what, or anywhere near all of what they've done. But that might give you the idea. Okay, let me think about some of these spin precession techniques. These can be very powerful, very high precision experimental techniques. So let me remind you. Here's my. I gave you before my theorist cartoon of an atom interferometer, an atomic clock, which was a far cry from the actual device with lasers and everything. So let me give you my theorist cartoon of how NMR works. Okay, similarly a far cry from how you actually do it in the lab, but this is sort of the basic idea, and we'll tell you how to look for axions. Okay, so basic idea: take a chunk of material, take a sample of material. These little purple arrows are supposed to represent nuclear spins. I do some amount of alignment of the nuclear spins as much as I can. Ideally order 1. That's something the NMR community has worked on for decades. Okay, they have some dipole moment mu. I'm aligning them with this big external magnetic field B, pointing this way. Okay, great. And so I've got some splitting between spin up and spin down. That's 2 mu B, right? Yes, question?
Order 1 so they don't mess with each other?
No, just as you'll see, order 1 to enhance the signal. So if they're all scrambled up, I don't get any signal from this. Yeah. Or not the signal I want. So there's a splitting between spin up and spin down, which is 2 mu B, right? So think this is just a 2 levels. Each spin is just 2-level system, simple quantum mechanics, 2-level system, right? And those are eigenstates, so they just sit there. It will just sit there until I apply my off-diagonal perturbation. So what you do in NMR is you apply your RF pulse. Okay, you shoot in some electromagnetic wave, oscillating like this. And what I care about in this case is the magnetic field, the B part of the wave, because that's what it'll interact with the spins. Okay, now. You'll notice, let's call this the Z direction or something. So let's say I talk about, that I polarized all these spins, let's say up in the Z direction to begin with. So up and down are eigenstates of the Hamiltonian until I turn on this magnetic field in the X direction, right? So then there's this Bx dot spin in the Hamiltonian interacting. That's an off-diagonal term in the Hamiltonian, right? Is that clear what I'm saying? So this thing, of course, will then cause this Rabi flopping, right? Or cause some spin precession, or whatever you want to say. It'll cause the spin to change. Up is no longer the eigenstate, right? Is that clear? Now think back to your undergrad quantum mechanics class. I suspect at some point you proved the following, which is if I tune the frequency. So you send in your RF pulse. If you're doing NMR in the lab, you have control of the frequency that you send in. So if I tune that frequency to be equal to the energy splitting between the 2 eigenstates, up and down, that's when you get your resonance, right? Remember back to your perturbation theory or whatever you did in quantum mechanics, right? That's the resonance. When the time dependence of the off-diagonal term in the Hamiltonian is equal to the energy splitting between the on-diagonal terms. Yes? That's NMR, more or less. Now there's a lot of complication to make that useful, but to me, to a theorist, that's NMR. Okay, that's the resonance. So is that clear? So how am I going to use that? Well, so what I'll do instead, the spins have some big, relatively big magnetic dipole moment, but what I'm looking for is their tiny little axion-induced electric dipole moment, right? It'll also point in the same direction. So now I'll have an EDM also pointing along the spins, yeah? Fine. Now I want to couple to that EDM. I need something that's gonna read that out, right? So I should apply an electric field instead of a magnetic field. In the previous example, I applied a magnetic field because that could torque the magnetic moments, but here I have an EDM, I want to look for that, so I should apply an electric field, right? But the really cool thing is I don't need to apply an oscillating electric field because actually all that mattered in the previous example was that the off-diagonal perturbation mu dot b was oscillating, right? Now I couldn't make mu oscillate. That's not how magnetic dipole moments work. But with the axion d is already oscillating. So I don't need to apply an oscillating E. I can just apply a nice static E, which is really big. I can apply a really nice big static E. Don't have to be limited by what I can apply as an oscillating field. Okay? And still, this off-diagonal term in the Hamiltonian, the d dot E, where the E points in this x direction, that'll be an oscillating perturbation. Is that clear? So that's like the heart of the idea for Casper, okay? Yes?
So what would the signal look like then?
Good. So what's the signal? Very good. So what happens? That's the next step. So, but I should say, notice that the frequency of the perturbation, so E is static. The frequency is the frequency of D oscillating, which is, of course, the axion mass. So then, this is a resonant experiment. It's on resonance when the Larmor frequency, which is just mu b, yeah, the energy splitting between spin up and spin down, when the Larmor frequency is equal to the axion mass. That's when I get my resonant enhancement, okay? So what I do is now instead of moving bars and cavities or something, I just dial the applied external magnetic field. And that sweeps through the possible axion masses, the possible resonant frequencies of this device. Okay? Is that clear? All right, so but what happens when I hit the resonance? What's my signal? Well, my signal is on resonance. I get the maximal spin precession. The spins start to tilt out of the initial alignment. It's nowhere near this much. It's really, really tiny. But if I have some very high sensitivity magnetometer, just like for ADMX or DM radio, all these spins, when they tilt, it's their dipole moment torquing on them, their electric dipole moment torquing on them, but their magnetic dipole moments, so a whole bunch of aligned spins in a sample is actually a magnet, right? So when they tilt a little bit, they produce some component of transverse magnetization of the sample. And that you can read out, okay? And of course, that's oscillating at this axion frequency, the Larmor frequency. So that's the big signal. That's the idea. So that's, in sort of very brief, that's the experiment, okay? Mm-hmm.
One step before, if electric dipole moment is pointing up and E is like this way, isn't it D dot E zero?
Yeah, that's true, but you're good point. Absolutely, that's right. That's true, but that's in the quantum mechanical Hamiltonian. And so what that'll cause, just like if I apply a magnetic field perpendicular to a spin, mu dot B is 0, but it just caused torquing of the spin.
That's coming from mu cross B.
Or, okay, so if you want to say it in the quantum mechanics language, remember the spin operator in the z direction projects to a sum of, a spin point in the z direction is also pointed in the x and y, just 50-50. Sorry, in the plus x and minus x, just 50-50, right? So it's the weirdness of quantum mechanics. You might think the spin is pointed only in the z direction. No. It's got some pointing in the x and y too, and the E will act on that. That's the quantum mechanics way to say it, yeah. Yeah, very good. No, these things are always very confusing, absolutely. And I switch back and forth between the classical and the quantum way of talking about it, which extra confuses. Yeah, great question. Yeah, thank you. Any other questions? Okay. So that's yes.
I'm not sure I understand the purpose of the electric field. I mean, it sounds like it's just this external B field competing against the axion field coming in. So what is the electric field doing?
Good. No, the external B field actually just sets the resonant frequency of this experiment. So it just lets me tune the Larmor frequency. I need to apply the electric field because it's E dot D. The term in the Hamiltonian is E dot D. That's where, and remember, D has my axion field. So I need to have something that causes D to have some physics I can read out. So this is what we thought of. There might be another idea, but this is what we thought of. I need something that can talk to a D. What talks to a D? An E. Okay, so I apply an E. That will then cause the spins to torque. If I don't apply an E, the spins don't torque.
I see.
And then I don't get any transverse magnetization, so no signal. Yes? Yes, they have to be, you can tell, because there's no other direction in the nucleus. By the way, as a small technical aside, actually I've been lying about all this. It's not the EDM you use in the nucleus because of Schiff's theorem. If you know something about that, that totally cancels out the effect of an EDM because there's electrons around it screening. So it's actually the Schiff moment. That was a technical side for those of you who knew what those words meant. Don't worry if you don't. But so I'm cheating a little bit, but the Schiff moment also has a direction set by the same spin direction. Yes?
I could come back to that formula for 1 second.
Mm-hmm.
So if you plug in Q2, that's kind of dark matter, and you plug in the EM
Uh-huh.
into the A, and
Uh-huh.
F photons and A is just the scale squared. Okay. Then you get like a really small number, like 10 to the minus 19. So I'm just,
Mm-hmm. You do.
Is it really possible to, I mean, given that the upper bound on the neutron EM is that scale there?
Yep. Great question. Absolutely. So I would say a few things in response to that. One, it's going to be very hard, for sure. Dark matter experiments are very hard, though. So we would need to apply. You'd need to get large sample sizes, very high precision magnetometers. You need to push the technology past where it is. Two, though, and this would be the reason that gives me some hope. Remember, I've got a resonance here, which was not possible with a static EDM. And I was telling you before, the width of my resonance is 10 to the minus 6, right? So I could, so long as I design an appropriately clean experiment, I could in principle get a million boost. So that helps me a lot right there. And then finally, I need a lot of things because this is a really small signal, so it's going to be hard anyway, even with all these helps. Finally, this is an oscillating signal at megahertz or kilohertz. If you have familiarity with any kind of these precision experiments, it's much better to measure an oscillating signal than a DC, static signal. There's way more, as you go lower in frequency, there's almost always more noise. In fact, it's a generic thing. There's 1/f noise, which basically means wherever it comes from, noise tends to grow, often at low frequencies like 1/f. So much better to look for an oscillating signal. That removes a lot of noise sources. With all that said, though, it's still going to be very hard to do. But dark matter experiments are hard. That does, by the way, if you plug in that root row of REM, it will show you why my sensitivity curve is actually getting a little better at low masses. We'll see that in just a second. OK, there's a ton of really important details, which are the main things to think about here. How do you actually build this? I'll skip them all, although I'm happy to go into detail later if you want. I've labeled this as E star, not E. Actually, I don't want to apply the electric field in the lab. I can do even much better than that. Much bigger than electric fields you can apply in a lab are electric fields that are already buried inside atoms. So you could use, for example, what's called a ferroelectric crystal, or any non-centrosymmetric crystal. So where the atom I'm caring about, the one that has this particular nuclear spin, is displaced from the symmetric position in the lattice. And then if you're perfectly symmetric, the E field will go to 0. But if it's displaced a little bit, you get these huge E fields, which are how strongly protons and electrons interact, which are pretty damn strong because they're really close, right? So then you can get some really big E fields in some of these ferroelectric materials, for example. So we'll want to use that. So for example, we'll use the material we're using right now is lead titanate. That one looked promising. And you need to do all sorts of you need to apply all the fancy techniques of NMR, all these fancy spin echo pulse sequences and everything to lengthen what's called T2. If you don't know about that, don't worry about that. But essentially how long these spins stay clean and following this theory cartoon like I pretended they were. Okay? And so on. So there's a whole lot of important issues and noise sources to take care of. Definitely not an easy experiment by any way, shape, or form. However, I'm going to skip all that. I will just quickly flash for you. You can make a projection for how strong the signal is and compare it to your magnetometer sensitivity. So make a projection for the sensitivity of such an NMR-based experiment. I won't walk through all this, just point out a few factors. You get a nice big boost because N is your number density of spins. Right? That helps the signal because the more spins there are, the bigger they all turn, and you just get a bigger magnetic field. And N is a nice big number, like 10 to the 22 per cubic centimeter, right? That's Avogadro's number coming in to help us, so that's good. This Dn is the Axion signal, and then P, I think Kevin had been asking about earlier, is the polarization fraction. So we do want to make that polarization fraction as high as possible. That's another hard thing. Let me skip, however, all the details. There we go. OK. And just since I'm running short on time, and I do want to tell you one last short thing for fun. This was the plot I showed you before for the E&M coupling. Now, here is a projection for futuristic projection for how far we think the NMR experiment could, in principle, go if you were given all the resources you needed and really push it to the max and things like that. But in particular, here's all I want to point out. Again, this is a resonant experiment, so I have to sweep frequencies to scan out this whole frequency range. Notice this is on a different plot because I have to plot it versus the GG dual coupling instead of the FF dual coupling. In principle, how you compare them is totally model dependent, but let me make the assumption that sort of, for example, if I'm looking for a QCD axion, I might care, just which portion of this QCD axion line do I cover? And you can see these two types of experiments, these two different types of couplings, two different types of ways of looking for the axion are very complementary, right? The electromagnetic experiments look at the higher frequencies. These look at the lower frequencies, divided roughly by megahertz or so. Yes?
What's the time scale for like resonance scanning here compared to resonance scanning as a
Great question. So I didn't say it at all. This was one of the too many things I prepared. But the time scale is actually what you choose. And the reason is you would usually choose to scan in about 10 to the minus 6 wide bins. And your experimental grad student doesn't want to spend more than about a year of data taking. 1 year of data, by the way, takes many years to collect in reality. So let's call it about 10 to the 7 seconds. So, and this is, notice everything I've just said has nothing to do with the mass or anything or which experiment I'm even talking about. It's just sort of a universal law that you get about 10 seconds per bin. So that's what you get. and I would say, by choice, we choose to take all the time we can possibly take. So we choose to use the maximum amount of time that we think we can run this thing for or whatever. Good, yes?
So you were saying before with the future projections, there was still like kind of some science to do also along with the money. Is that true for experiments like Casper?
Absolutely. Oh, yes. And for several years now, we, but not really me, has been heavily involved in doing that, in building sort of proof of principle type experiments, absolutely. Oh, sorry. Choice again. We're scanning, and so we choose where to stop. But I should say it gets much harder to go below this for a whole bunch of reasons. As I mentioned, lower frequencies get ever harder. So this sensitivity curve, if you tried to go lower, would turn up rapidly. We're sort of aiming at this canonical QCD axion window, which goes down to about 10 to the minus 12 eV. But also true that that's a good frequency range for this type of technology, and there's just much more noise at low frequencies. Then you get back closer to the static EDM type experiments. It gets harder and harder to resonate and more noise. Sorry.
It looks like your sensitivity is getting worse as you get higher frequency.
Good. The real answer, you can see it's doing some funny curving things. So the real answer is a little bit complicated. I could maybe tell you that a little after. But one trivial, you're always lying a little bit when the actual answer is a product of many things and you talk about only one factor, right? That's just a lie, but I'll do it anyway. One trivial factor you can see is this A naught is root rho over M. And we didn't have the derivative canceling that out here. So we just won that. So that's a part of what's happening here. These breakpoints and things like that have to do with the T2, the NMR, like the spin coherence time we've assumed and things like that. So important but technical details, maybe I can tell you about that afterwards. But definitely important. Yes?
In both of these plots, it appears that the sensitivities are hardly going below QCD axion.
Right. We would usually, this one wasn't done quite as carefully. These were done carefully because we would just say we choose not to go below. We spend as much time at each frequency as necessary to get down there, then we move on to the next frequency. So we want to use our time as well as possible. If that's as well as possible, if you believe your prior probability for where dark matter is sort of peaked along this line. I constantly harass ADMX since they've actually got results on this, and I'm a theorist, so it's my prerogative to draw plots like that and yet harass ADMX. For not quite going low enough, in my opinion. As I've told them many times, I don't think anyone's going to go back and cover the region they've covered, and I think they should go a little bit lower to really, boy, wouldn't it be sad if the action was just a little below there and we miss it for all time because no one's going to get money to go back and redo what they already did. Anyway, that was an aside. All right. Let me go on. Or was there any last questions on this? Please, yes.
If you plug in rho over M, but you have also an FA in the bottom and the product of MA times that. So doesn't the M disappear?
Good, that's right, but then you're sliding along this line. So you see what he said? So he said, that's great, thanks for pointing that out. So if I write 1 over M, right? MF is a constant, which is actually just the statement that this line is a linear line, right? So indeed, as I slide along this line, from what I've told you so far, our sensitivity curve, the blue of the NMR, should exactly be linear and track this line. And that's what it would do. Right? That MF is a constant, so as I change F, nothing changes. I just slide right along this line. Okay, notice, by the way, this is not in 1 over F, this is in G, to be confusing. Or I mean, sorry, I didn't say that very well. Changing F, but keeping this mass relation of the QCD axion means you're sliding along this red line.
But doesn't at the end the sensitivity should be the same?
Should be the same, yeah. So absolutely, and look, it kind of roughly is, yeah? I mean, this one is very flat, and this one is roughly linear. Now, maybe you're seeing there's a small tilt here. Those are these technical factors I was pointing out that I haven't talked about, which are important, integration times and things like that. But roughly, if you squint, it's roughly linear. So that indeed is working. Good point. Thank you. OK, excellent. Any last questions on that? All right, that sort of concluded what I wanted to say about, well, I had a lot more to say, but about ultralight dark matter. But I want to go on and tell you about something that at least sounds completely different about our ideas for gravitational wave detection. This doesn't really have anything to do with the title of my lectures, but I just want to talk about it because I like it. However, as I've been kind of building up all along, actually there is a lot of overlap between looking for gravitational waves and looking for ultralight dark matter, right? In fact, we said looking for some background, gravitational waves, some big background metric perturbation is a lot like looking for these background scalar or vector fields. Okay? So with that flimsy excuse, I'll totally switch topics. And just in the last 15 minutes or so, try to tell you about some of our ideas for looking for gravitational waves. By the way, these do actually connect. In fact, they're similar to the atomic clock and other kind of ideas I told you about for looking for ultralight dark matter in the beginning. So in fact, actually, these exact same type of experiments we're designing can also look for certain kinds of ultralight dark matter. If we have time, I can even show you this experiment we call MAGIS is for detecting gravitational waves, but also I can show you its own, the exact same hardware, sensitivity to ultralight dark matter. So there is some connection. All right. So the gravitational wave signal is very small, right? In fact, let me say when a gravitational wave comes through, so it's there, sourced by some black holes or something oscillating, orbiting around each other far, far away in the universe. Gravitational wave propagates out, and in the lab I have two test masses. And when a gravitational wave comes through, right, I see the test masses stretch and squeeze like this, jitter back and forth, right? That's the signal of the gravitational wave. It's a really tiny signal. In particular, the length between the test masses goes something like this, where it's roughly not changing at all, but at some tiny amplitude, where this h is some tiny dimensionless number called the strain, and this omega is the frequency, OK, this distance is changing, right? All right, well, how could I look for that? Well, looking for length changes is actually very similar to looking for time changes. In fact, that's essentially what LIGO does. It sends lasers across the baseline, looking for a length change, really by timing, if you like. Well, this is a crude way to say it, but by the change in the time it takes the laser to get across the baseline. So I might think that a good clock was a good way to go. So let me ask, OK, can I use these atomic technologies, the atomic clocks or atomic interferometers, to look for gravitational waves? How would that work? OK? And so let me tell you a little bit about some of our ideas for how you might do that, though there might be other ideas too. OK. So first to do that, I have to tell you just a little bit more about how the atomic clock works. So remember, I already told you, I start with my atom in state 1. I split it into the superposition of 1 plus 2, right? There's some beam splitter there. I wait some amount of time. Then I apply a final beam splitter, read out the phase, blah, blah, blah. Right? That was the atomic clock. But as many of you actually asked me, I didn't tell you how you make this beam splitter. It seems sort of magical. Now I need to tell you how you make that, OK? So I can actually show you how we would design a gravitational wave detector. So how you make the beam splitter here is as follows. So let's say I have these two states, 1 and 2. Right? Well, I have some energy splitting between them, delta E. I want something that's going to cause some state change from 1 to 2, right? So the trick, at least with these optical atomic clocks, is to shine a laser light that's resonant or roughly resonant with the transition here, OK, between these states. When you do that, it's actually sort of the same thing I was just talking about. I have some two-level system, 1 and 2, right? They're eigenstates when the laser is off. They're the energy eigenstates of the atom, right? But when the laser is on, they're coupled, so that's an off-diagonal term in the Hamiltonian, right? So you know what it's going to do, this laser that's shining on the atom. So here I have my atom, and then I shine some laser light on it, OK? Well, you know what it's going to do? It couples these two states, so they're going to Rabi flop, right? They're gonna flop back and forth into each other, right? Think back to your same sort of quantum mechanics we were just talking about, basically, right? So okay, how does this work? Well, in particular, let me plot it a little more precisely. If let me say the wave function of the atom is C1, 1 plus C2, 2. Well, let's say now I'm plotting the C's. Let's say the atom starts here. This is a function of time. Let's say the atom starts entirely in state 1, yeah? At the beginning of the experiment, t equals 0. Well, once I turn on the light, so C1 starts up here, and C2 starts at 0. Once I turn on the light, they'll begin to Rabi flop. So you know, if you remember the quantum mechanics, that it looks sort of like that, right? In fact, after I've waited, this would be called pi radians in units of the Rabi frequency. After I've waited a pi amount of time, okay? By the way, the Rabi frequency is really in terms of things like the transition dipole moment and the intensity of light, blah, blah. Let me ignore that for a second. But after I've waited this amount of time, the atom is entirely flopped from state 1 to state 2. Okay? Mm-hmm.
So my concern here would be if you waited a number of integration times, like say you like waited a longer integration.
Mm-hmm.
If it's like compare it to the size of like the frequency of the gravitational wave, it might just average out. Like you'd stay synced. So how would you know?
Good. So great. So a great question. So the way I'm going to use it is I'm going to use this only to send very short little pulses of light, and that's going to make the beam splitter. And then the waiting time is time with the laser off, so they're not flopping. And that's very important. And in fact, for other, not so much for gravitational waves, but for other effects, that sets an upper frequency. You can't look for an effect which is fast compared to this time, because then it's not like a really short beam splitter and then I get to wait. So you're absolutely right. This time would set a lower limit. But for example, with normal atoms that we use and reasonable laser intensities in the lab, this time can be easily about a microsecond or so. So it's really a short little pulse compared to the frequencies I'm going to be talking about for gravity waves, which will be more like a hertz. But great question. Yeah, absolutely. Okay, so if I waited this half a Rabi flop, it's gone entirely from state 1 to state 2. But look, if I give what's called a pi over 2 pulse, so if I turn the laser on for that amount of time, it goes to a superposition. It goes to this. So that's a beam splitter, also called a pi over 2 pulse in this NMR type lingo. Okay, it moves the state from ground state to linear superposition of the two. Okay, is that clear? All right. Then the final beam splitter is the same thing. It's another pi over 2 pulse. We'll actually use a much more complicated pulse sequence than just beam splitter, wait, beam splitter. I think in the interest of time, I won't tell you about that, although I'm happy to tell you about that later. We'll also use pi pulses that switch the state and things like that. But this is the basic idea, okay? So I have my atom sitting there, my ultra cold atom or atom cloud sitting there, and then I interact with it by sending pulses of light. So that's how I run the whole interferometers, by setting some set of pulses of light to split the wave function of the atom and ultimately recombine it, read out the interference. Okay? So is that basic idea clear? That's what we need to understand, the basic idea of the chapter. Okay. Good. So let me think about how to say this. So for a gravitational wave, you know that this signal, I want to see this strain, but you can see the size of the signal is, of course, proportional to the distance between my two test masses, or proportional to the size of my experiment, right? So of course, for a gravitational wave, I want as big an experiment as possible. That's why LIGO's 4 kilometers long, right? It's not super easy to send ultra-cold atoms over kilometer distances. What we can send over kilometer distances are lasers, right? That's what LIGO does. That's not too hard. That's why it's crucial we're using a laser here as the beam splitter. Our basic proposal then is to run 2 atomic clocks. An atom here, an atom here, okay? On the ends of some very long laser baseline. So I'm sending laser light all the way across this baseline. And in fact, very crucially, a crucially important detail here is that I use the same laser to drive both atom interferometers, or both atomic clocks. Okay, that's crucial for canceling noise. There's a whole long story there I'm happy to tell you about later. Let me skip it all now, although it's really the heart, like without that this doesn't work. That's sort of why this works. But in the interest of time, let me skip it and just say, okay, just trust me for now that if I run these 2 atomic clocks with the same laser pulses, shot from one side, for example, I'll be able to remove common mode, reject a lot of the noise. Okay? Now, how do I look for gravity waves with this? Well, the idea then is as follows. Oh, question, yes?
By the same laser pulse coming, so I shoot it here, then I use a beam splitter, then I send part of the beam split to the other side?
Ah, great question. No, I'd be very afraid. So the question was, do I use a beam splitter to split the laser pulse and send it to one end and the other? No, some people have proposed that. I find that I'd be very worried about doing that. Well, I'm not going to get into noise too much, but let me say a crucial noise source for these are brutally small signals. So any little thing that wiggles your test mass is a disaster. So LIGO, for example, works super hard to isolate their test masses from the Earth, but still, nevertheless, there's seismic noise shaking their test mass, and lots of other things shake the test mass. If we interacted with the atoms using 2 laser pulses that were split, then I'd be very worried about that one splitter. That's the one thing that's uncommon between the two, right? I'm really going to subtract the outputs of these two and really try to use common mode cancellation to get rid of lots of otherwise absolutely terrible noise. Any one thing that's uncommon, a big macroscopic piece of stuff, shakes and jitters like crazy. There's just no way, stuff jitters. The Earth jitters, everything jitters.
You wouldn't be able to use the same beam splitter to like the one pulse that goes partway through and partway through.
I want to have nothing, after the laser hits this atom, I want to have nothing but vacuum until it hits the next atom.
Right.
So that's the critical thing. So however you produce the laser is fine, but then one pulse that flies straight through them both. Does that make sense? Because I want nothing in the way. I want no optical elements that might introduce noise.
Okay, what I was suggesting was like to use the beam splitter first.
That's fine, yeah, although we don't, well, there's a lot of complicated optics that go into running this, let me say. It's not quite as simple as this picture. Okay, now, there's actually, and this brings up a sort of crucial point, which is the following, which is, what's my picture of how to use this to detect gravitational waves? Well, a sort of crude picture of a gravitational wave detector would be I have 2 good inertial test masses. I try to make them as noise-free as possible. I have some laser or something going across the baseline between them, and I have a good clock to time how long it takes, right? And I would argue this is basically how LIGO works. They have their 2 test masses, let's say beam splitter and mirror. Laser light goes across the baseline. You would absolutely have a signal in one arm of LIGO, no problem. That arm stretches and squeezes. But the laser is nowhere near a good enough clock. Lasers are pretty good. We work really hard, but nowhere near good enough to see the tiny gravitational wave signals. So I need to cavity stabilize, if you like, that laser. In other words, I need to use this second arm to compare to, okay, to subtract out all the common mode noise, which is all the terrible noise from the laser. Both laser has all sorts of jitter on their phase fronts or frequency noise, and also the actual physical jitter of the device. So I would argue LIGO works the same, where their mirrors the test masses, the laser is the baseline, and the second arm is the good clock, roughly. I would describe our gravity wave detector in similar language, but here notice something interesting. I'm using our atoms as our initial test masses. Okay, the laser, of course, goes across the baseline here, gives me the long baseline. I'm also using the atoms as the good clock. So they're doing double duty here. This is critical. It's a little bit different from some other people's proposals for how to use atom interferometry, but we think this has a real advantage. We think this is really positive. In particular, some people just think about using atoms as the good clock. However, it turns out you can also use atoms as the inertial test masses. I'm really not going to talk much about this, except to say that I can actually, I've told you how to run an atomic clock. That's not actually the pulse configuration we run this atom interferometer in. We run it in a configuration which makes it an accelerometer. So the atoms are actually really reading out, the atom interferometers are really reading out their acceleration. So they really are the inertial test masses. Yes?
So is the squeezing and stretching that you're looking at squeezing and stretching in space or time?
Well, in some sense, I would say both. But let's say if I work in a particular frame, like let's say I'm sitting in the lab frame, then you can think about it as stretching and squeezing in space, for example. Yeah. But it's also really, of course, in the time it takes the laser to get across and back, which is really my signal. I'm using these atomic clocks to time how long it takes the laser pulse to get across and back. Notice one interesting difference, which is from LIGO. Here, it really is the laser which is doing the interfering. Yeah, LIGO is also an interferometer, but it's the laser interfering. For us, the laser is not doing any interfering. It's the atoms that are interfering. I'm really splitting the atoms' wave functions and recombining them. That's what this little cartoon is supposed to say. Okay, so just like I told you, I really am splitting the atoms' wave functions and recombining them. But here, they're acting like the inertial test masses and the clock. It's a funny and interesting difference, and will actually allow us to do single baseline detection instead of needing two baselines, which can make some practical differences for how your detector works.
So
Please, yeah.
Atoms really move in space, or they are fixed in position?
Great question. Okay, you're asking great questions. This is why I would normally give a whole talk on this. There's a lot of important things here. So you're absolutely right. And in fact, one thing I didn't tell you, but you can already see it here, and it's actually a very important part of the experiment. Let's say the atom starts in the ground state, yeah? When I transition it to state 2, that's also called absorption, right? The atom has absorbed a photon and hopped up a level. Well, you know what's going to happen. If the atom absorbs the photon, it's going to get kicked. It's also going to move in space. Similarly, when I go back from 2 to 1, that's stimulated emission. It shoots out a photon. It's going to get kicked the other way. So absolutely, so I'll show it since you asked. Here's a space-time diagram of what our things look like. So this is the time versus space. Just look at one of these little diamonds. This is actually the space-time diagram of what's really going on with our atom interferometer. And these little wiggly things are the light pulses. You can see, don't worry, this is a lot of details. I'm not going to go into this all. Don't worry about the complication of this diagram. Just focus on the one following feature. See these two paths? Those are the two halves of the wave function. Because of this kicking effect, right? This half of the wave function is moving with respect to this one. Exactly as he says, right? So they will separate in space. That's actually a critical part of making an accelerometer in a way that I'm not going to tell you at all. So is that clear? Yeah, so is that point clear? Because that actually is an important part of the story. Is that questions on that? In fact, you might believe, so these are the two arms of the interferometer, okay? The left arm and the right arm there. The more you can separate those two arms, the better a phase shift I'm going to have. Hopefully you can, I'm waving my hands here, but hopefully you can believe that. Right? If I didn't separate them all, you can believe, okay, there wouldn't be much phase shift, right? Like if I in LIGO, I lay the two laser arms on top of each other, that would be pretty stupid, right? So I want to separate these arms as much as possible, which means getting as much as possible spatial separation of the two halves of the atom's wave function. All right, now the really cool, I just have to show this because I think it's so cool. The really cool thing, when we started this whole project many, many years ago, when I was a grad student actually, started this. Then at that time, so one measure of how sensitive your device is how much you've spatially split these halves, okay? At that time, you could spatially split the two halves of an atom interferometer by a very little bit, okay? Very short little distances. Now, and we knew we needed to do much better than that. Let me actually just show you this plot. If I can find it real quick. Here it is. They've worked very hard. Ignore these other things for a second. And they demonstrated, here's this 10-meter drop tower I showed you a few lectures ago, running an atom interferometer, letting the atoms fall along this drop length. They worked very hard to demonstrate the following. They did what's called large momentum transfer beam splitting. So not actually the way I told you, but a fancy AMO trick that does much effectively, coherently transfers many, many, many photons. Okay? And this down here is honest to God real data. This is a picture of the atom interferometer at of the atom's wave function at maximal separation. Of course, once you take the picture, you've spoiled the interference. So that shot doesn't work, but just take the picture once. Otherwise, keep your eyes off. Don't look. This is the atom's wave function. This is real data. And it has these two spikes. These are the two halves of the atom's wave function that you split with this beam splitter. And they're half a meter apart. They're like this. Like I can stick my hand between it. It's by far the world's most macroscopic quantum superposition, quantum wave of matter. Light you can split more. But of actual atoms, I can take an atom and put half of its wave function here and half of its wave function here. And this is the picture of it. This is the real honest to God data. Okay? Well, this is actually stitched together, but trust me. So that's pretty darn cool, and it's just a fun example for any undergrad quantum mechanics class. You can stick your hand through this macroscopic superposition. And so long as you don't look at it, you don't collapse it. You can still measure the interference. Okay, that's a fun demonstration, but also the reason why they were really interested in doing it was this was crucial. This was the level of technology we needed to get to have a hope of looking for gravitational waves. So let me just summarize and say they've done a heck of a lot of really good work. developing this technology. There's still some more to go. But we think you may actually be able to build, in principle, in the future, a feasible gravitational wave detector with this. And I'm really excited to say that we've finally, just a few years ago, got funding to actually try to do that. Well, actually, first we're building a mini little 100-meter version, sort of like LIGO has their 40-meter test bed. You want to do this first to prove before we can go to the kilometer scale. This is a extra air shaft at Fermilab to the neutrino beam, actually. So it leads underground the neutrino beam. And the people who had this air shaft were happy to carve off a piece of it. It runs 100 meters down. And so at Fermilab, we're building a 100-meter, evacuated, magnetically shielded, magnetically controlled, et cetera, nice region to run these atom interferometers or atomic clocks. There'll be atomic clocks at each end, and there'll be a long, the laser will be running across this whole baseline here. This will actually just be a proof of principle experiment, although I think once we get it working, if we can get it working, I think that will give us a strong case to go to the next step. The Magis, we call this Magis 100. The Magis 100 collaboration is hoping to get this working in the next few years, 3 or 4 years or so. We'll see. That's probably an aggressive timescale. And I'm excited to say it was sort of in the beginning, we kept telling everyone how excited we were about using atom interferometry and things like that to look for gravitational waves. And it was sort of lonely. But by now, actually, a lot of groups have gotten excited about using atomic technology to look for gravitational waves. And there's a number of these 100-meter class detectors springing up around the world, including, for example, Aeon in the UK, MIGA in France, and Zyga in China. I've written the parameters here, but you can see they're all around 100 meters or so. They have somewhat different atoms they use, somewhat different techniques, but they're all basically trying to prove that we can develop this kind of technology we need to look for gravitational waves. Yes?
Why is the orientation important enough to put on that little table?
It's more technically important. It makes a big difference for the kind of backgrounds you have to deal with and how you have to build it. So we prefer the vertical orientation probably, although horizontal may work as well. But horizontal can introduce rotation of the Earth backgrounds. I could tell you why sort of in more detail later. But it does introduce separate backgrounds, although maybe there'll be practical reasons horizontal is easier too. So it's a trade-off. Yes? No, they would be very much overlapping. And in fact, this little cartoon graphic here is supposed to say just that. So I didn't show you. I'll show you. Just give me 10 more seconds. I'll show you a sensitivity curve. But the idea is, just like how LIGO and Virgo and Kager, you want to build multiple gravitational wave detectors in the 100 hertz or so band. These detectors would be around the 1 hertz band, the band below LIGO and above LISA. You probably also want a network of those. You want multiple ones. And in fact, Magis and Aeon are being directly designed to directly be a network and collaborate. So I think it's great that we have all of these, aiming to prove the same technology and work in the same band, just like with the many LIGO and Virgo and everything. Let me just sort of flash here. Final thing. Here are some sort of projections for sensitivity. Here's LIGO. This is strain per hertz versus frequency. Here's LIGO. Here's LISA. Here would be on the ground. That's what we're aiming to build proof of principle detectors for now. Maybe well into the future. I could think about also a satellite-based experiment for this, which would allow me to go even lower in frequency. And it would hopefully be able to carve out this intermediate frequency band between LIGO and LISA, where I didn't get a chance to talk about it. Here are some example sources, for example, that fit in there. But there's a lot of really interesting science in that band. So actually, a lot of what I've been doing recently is thinking all about new signals that can fit in that band. And I encourage you, if you're interested, to think about this, because people spend a lot of time thinking about what you see in LIGO and also what you see in LISA, much less time in this intermediate frequency band. So I would say every time we started trying to think of something new, we realized there was something new that people hadn't thought of yet as interesting gravitational wave science you can do in that band. So let me close with that motivation to you to if you're interested, think about that. I'm happy to tell you more about that later. All right, thank you. And I really appreciate this. Thank you. I just want to say I did really appreciate all these lectures, and I really appreciated how excited you all were and all the questions you asked. That was really great. Much better than me just talking for 5 hours straight. Please, I'll stick around a little bit longer. I do have to leave in the middle of the next lecture, unfortunately, to catch my flight. But for the next half hour or so, happy to stick around and chat or whatever. So please feel free to come up and ask more questions. That's great.